Hello Honors Pre-Calculus students, this is Mr. Gazzato, and today's learning target is to solve polynomial inequalities by factoring. Now I know we covered domain of inequalities back in the first unit, so this should be familiar. If you look at problem numbers 1 and 2, what is the main idea? Well, we need to factor by grouping. So if you look at the problem number 1, and you were to group the first two terms, you can factor out an x squared. So x squared times 2x minus 3 minus 5 times the quantity 2x minus 3. Now remember, when you factor by grouping, these two terms that I just highlighted in yellow always need to be the same. So this becomes x squared minus 5 times 2x minus 3. And if we were to factor into linear terms, x minus the square root of 5, x plus the square root of 5, and 2x minus 3. And just in case you didn't know where I got the x minus root 5, if you set this factor equal to 0, you get x is equal to plus or minus root 5. So without graphing this using technology, we could put these critical points on the number line. So we're going to put root 5, negative root 5, and then we also need 1.5. Now root 5 is a little bit bigger than root 4, so I know 1.5 is to the left of root 5. Then we're going to test each interval. So what we did in class is we picked a number bigger than root 5. Suppose we pick 10. Each factor will be positive, so overall to the right of root 5 it is positive. If you think about multiplicities of zeros, the x-intercepts are on the number line there in blue. The graph goes through every x-intercept. So if you use the idea of multiplicity, you should be able to realize that this is minus, plus, and minus. Now if you don't like that method, you can pick a number between 1.5 and root 5, say 2. The first term is going to be negative, positive, positive, so you will get a negative result. If you pick a number between negative root 5 and 1.5, say 0, negative, positive, negative, so the result is positive. Likewise, to the left of negative root 5, say negative 10, negative, 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 so the result is negative. So the goal was to find when this inequality was less than 0, so a strict less than. So you cannot be any of these points, so I'm going to use open circles. So I'm looking for negative, so negative infinity to negative 5, root 5, union 1.5 to root 5. I'm going to pause the screen, and if you want to try problem number 2, go ahead and try problem number 2. If you look at problem number 2, I factored by grouping, so 3x minus 4 was in common. And when I look at this polynomial, x squared plus 4 is always positive, so there are no critical values on the number line. So the only critical value I have is 4/3, and when I checked to a little bit to the right of 4/3, I got a positive, and to the left negative, so 4/3 comma infinity. At this point you can try the next problem, number 3. Okay, for problem number 3, you should notice that each of these terms have an x, so I factor out an x first. After I factored out the x, I can look at this that I highlighted in green and factor by grouping again. Notice here you need to take out the negative to make the x minus 2 the same. And then it factors into this sentence here with the little black dot. I went over to the other side and I solved that equation, 5x squared minus 1. So if you wanted to factor it into completely linear factors, it would be x and then x minus root 5 over 5, x plus root 5 over 5, and then x minus 2. But if you were to multiply this out, you will not get the leading coefficient of 5, so you would need to put the 5 out in front. So I did this down at the bottom only to talk about factoring completely. The goal of this problem was to solve the inequality. So what you want to do now is test each part of the number line. So if you pick a number bigger than 2, each term will be positive. So all these terms will be positive. So the overall result is positive. I personally like to use the idea of the multiplicities of the zeros. So since all of these x-intercepts go through, we're just going to alternate signs. However, if you don't like that, you're more than willing to, or more than, you can definitely test each interval if you do not like the alternating signs and using the x-intercepts. For problem number 3, hopefully you realized each of these terms have an x, so I factored out the x. And then I was left with a cubic, and in that cubic you can factor by grouping. The common term is x minus 2, and then I get down to this blue part here. And then if you look in red, I solved 5x squared minus 1. I got x equals plus or minus root 5. So if I come down to the black sentence down at the bottom, that's how it completely factors. However, if you look at the yellow equation, there is a leading coefficient of 5. So right now, if I multiply the black equation, I only get x to the 4th. So I definitely need to put a 5 there. So this is how the inequality would completely factor down at the bottom. So at this point, I'm going to test each interval, pick a number bigger than 2. Each of those terms are going to be positive, so the overall result is positive. I personally like to use the multiplicity of the zeros. Since all of these exponents are 1, I know the x-intercepts, the graph goes through every x-intercept. So this is a minus, plus, minus, plus. You can always test each interval by picking a number. I'm going to pause the screen if you would like to try problem number 4. Okay, we needed to finish number 3. So we want to know when this is less than or equal to 0. So each of these points are going to be solid dots. And then I'm looking for the negative intervals. So it would be bracket negative root 5 to 5, comma 0, union root 5 over 5 to 2. I'm going to pause the screen. You can try problem number 4. I'm going to show the answer then, or you could just go to the next page, which has a different type of problem called quadratic-like problem. Okay, you can take a look at problem number 4. Again, factor by grouping. It is similar to problem number 2, and I'm going to move on to problem number 5 now. Okay, problem number 5 is quadratic in nature. So when you look at number 5, you should see it factors. It is very similar to a squared minus 12a plus 32. The only difference here is a is acting like x squared. So the red equation, what two numbers multiply to 32 and add the negative 12? So that would be a minus 8 and a minus 4. So when you look at the polynomial inequality number 5, this factors into x squared minus 8, x squared minus 4, that's greater or equal to 0. And then this factors even further. And if you were to solve each equation, x squared is equal to 8, x squared is equal to 4, x is plus or minus root 8, x is plus or minus 2, so x is plus or minus 2 square root of 2. So to factor this completely, which is something we do want you to know, this would be x minus root 2, x minus 2 root 2, x plus 2 root 2, x minus 2, x plus 2. So we're going to draw the number line here, and we're going to put all the critical values. So we have 2 root 2, negative 2, and negative 2 root 2. The multiplicities on each of these is 1. We want greater than or equal to 0, so I'm going to have solid dots on all these. And then I'm going to pick a number, say 10. Each term will be positive when I plug in 10, so the overall result is positive. And as I said, the multiplicities are 1, so it goes through. So this is a minus, plus, minus, plus. And since we're interested in the greater or equal to 0, we want negative infinity to negative 2 root 2 union. And that should be a bracket. Union bracket, negative 2 to 2. Union 2 root 2 to infinity. I'm going to pause the screen and you can try problem number 6. Okay, take a look at problem number 6. See if you agree with my factoring and my number line approach. And then in number 7, it's also quadratic-like, but the factoring gets a little more complicated, so we're going to take a look at number 7 next. Okay, for problem number 7, if you're not very good at factoring, you could think of this as the quadratic formula. I'm actually going to do it both ways. But if you think of this as 3y squared minus 13y minus 30, you can use the quadratic formula here. So you would have the opposite of b, plus or minus the square root of b squared minus 4ac all over 2a. So go ahead and get your calculator out and calculate that discriminant. Okay, so when you do that, you get the square root of 529, and that's a perfect square, so you get 13 plus or minus 23 over 6. And this really means two different answers. It's 13 plus 23 over 6 and 13 minus 23 over 6. So doing that on my calculator or in my head, the first fraction is 6, and 13 take away 23 divided by 6 is negative 1.6 repeating. I prefer fractions, so we're going to say negative 5/3. So when you use the quadratic formula here, you're actually solving for x squared. So this is x squared equals x squared equals. So x squared is equal to 6, or x squared is equal to negative 5/3. So if you were to write this as a factor, it's x squared minus 6, and then x squared plus 5/3 is greater or equal to 0. However, the leading coefficient is not the same, so I need to put the 3. So that's one way to factor it into quadratics. And if you were to go a step further, you're going to get some imaginary numbers. Now I'm going to show you how to factor this without the quadratic formula. Okay, let's suppose you didn't want to use the quadratic formula here. And if you look at this equation, 3x to the 4th minus 13x squared minus 30 greater or equal to 0. So if you're good at factoring, you need to put a 3x here and an x here. And then you need to figure out the combinations of factors of 30 so that middle term adds up to negative 13. Eventually you'll realize that this is going to be plus 5. And then, this should have been x squared on both of those. And then x squared minus 6. And if you were to multiply this out, just kind of double checking that, you do get the minus 13x squared. So if you look at the green here and you look at the original, if you were to distribute the 3, you'll see that those are mathematically equivalent. So the goal here is to solve the inequality. Here you get imaginary, so there are no x-intercepts there. And then from this one, you get x squared is equal to plus or minus the square root of 6. So instead of factoring this one completely, I'm just going to use those critical values, square root of 6 and negative square root of 6. We want a greater or equal, so we're going to have some solid dots. If you were to plug in a number bigger than root 6, and I'm just going to use this blue highlighted equation here, you will get a positive number. And then if you were to plug in 0, you're going to get a negative number. And if you were to plug in like negative 100, you will get a positive number. So the goal was to find greater than or equal to 0. So then we've got negative infinity to negative root 6 with a bracket, union, bracket, root 6 to infinity. I'm going to pause the screen and you can try problem number 8. All right, if you look at problem number 8, I just used my factoring skills and I got this green highlighted factoring. The first term has imaginary solutions. The second term has x equals plus or minus 1. I put those values on the number line, tested each interval, and came up with this as my final interval for that inequality of a strict less than. So hopefully you found this helpful on solving polynomial inequalities. We did it back in the first unit, and we've been working on polynomials in our factoring skills this unit.